Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. So far we have been looking at mode shapes and resonances or natural frequencies. We found them either in some exact sense right from the partial differential equation or in an approximate sense using Rayleigh rates. Now once we have the mode shapes and the resonances, we can go for the forced response. Okay, so we are more or less at the point where we can tackle what we want. Okay, in vibrations we want to know if we force the structure what kind of response we get. Okay, so firstly let me start something here which is important. If I have a simply supported plate, okay, and I will write the PD in a special form minus D del 4 W del x4 plus twice del 4 W del x square del y square plus del 4 W by del y fourth. This is the spatial operator, okay, spatial operator. Let me call it L3 because it is in the transverse direction, minus rho h w double dot is 0. Okay. Now the mode shape for a simply supported case is phi mn is equal to sine m pi x by a sine n pi y by b, and the response in a single mn mode shape Wmn x comma y comma t, the free response is phi mn x comma y at the resonance frequency, natural frequency. Okay, so if I substitute this in there, okay, what I will get first, let me write, is minus D del 4 by del x4 plus 2 del 4 by del x square del y square plus del 4 W by del y, del y4 operating on phi mn x comma y. The time term comes in omega mn t minus rho h double dot, rho h w double dot. So that becomes minus rho h Wmn double dot, the derivative is on the time term, so I get minus omega square mn phi mn e to the power of j omega mn t equal to 0. So I take this out. Okay. So if I consider this as the L3 operator, L3, why? Because it's in the alpha 3 direction, alpha 3 or W is in that direction. Okay, it is about the z directional response. So this L3 acting on phi mn becomes equal to minus rho h omega square mn phi mn. Okay. Okay. So this is one thing we should remember. Should remember this, because the reason I am doing it is that the forced response section begins with this operator. Okay. So the L3 operating on a mode shape, however complicated it is, for shells it is even more complicated. This is the L3 operator acting on the mode shape, is just equal to minus rho h natural frequency squared phi mn. So whenever we find this, we are going to replace it with this, so that should be remembered. The other is, if we actually put in the phi mn form, which is sine m pi x by a sine n pi y by b, then I get minus d m pi by a whole squared plus n pi by b whole squared phi mn is equal to minus rho h omega square mn phi mn. This can go. Now this gives me a formula for natural frequency. Okay, so my omega mn is now square root of d by rho h m pi by a, so this has to be a further squared, m pi by a squared plus n pi by b squared. This is 2. Okay, so these two things should be remembered. Okay, now we are into this section of forced response. Forced response of plates and shells. Okay. So now we are going to expand the displacement as a weighted sum of the mode shapes. Okay, mode shapes, why? Because this set of mode shapes is one orthogonal, the other they are complete. Okay, every displacement with all the possible boundary conditions are representable by the mode shape, and so they form a complete set and they are orthogonal. So now what do we do? if we have a curved shell, we have, let us say, a cylinder, okay. Cylinder has axial motion, cylinder has torsional motion, cylinder has motion in the alpha 3 or z direction. So, any point can have axial movement along with torsional movement along with radial outward movement. Any single point sees all three motions at the same time. So, it is complicated. So, a shell mode shape, for example, could be cos m pi x by L cos n theta in the x direction, in the theta direction it could be sin m pi x by L sin n theta, in the transverse direction it could be sin m pi x by L cos n theta, and this could be the amplitude, this could be the amplitude, okay. In the mnth mode, okay, all these will have mn subscript, okay. So, now this together is the mode shape. In a single mode shape, this is how a single point at x star theta star, let us say, moves. It has this displacement in the axial direction, this in the torsional direction, this in the transverse direction. So, these three expressions together are one mode shape. They are not three mode shapes, one mode shape, okay. So, how do we now represent? You say I takes values 1, 2 and 3, 1 will be for axial, 2 for torsion, 3 for transverse, okay. That means x direction, theta direction, alpha 3 direction. So, ui will be represented now, ui which is a function of alpha 1, alpha 2 and t, okay, is represented how? In the response. We are representing it in the response as a sum of mode shapes, okay, with an amplitude that depends on time. This is called the modal participation factor, modal participation factor. That means how much of a single mode contributes to the total response, okay. So, this mode will have a modal participation factor eta mn of t, one modal participation factor, and this is the I displacement. So, the mode shape has to be represented accordingly, I direction and the same mode shape, okay. So, for example, for the same cylinder example, u1 which is axial, okay, will be summation over mn now, eta mn, then a mn by c mn cos m pi x by L cos n theta, okay. So, this is u1k now, this is u1k according to this formula, u1k. Then u2 which is theta, torsion, is again sigma mn which take the place of k here, same participation factor, this is a function of time. Bmn by Cmn sine m pi x by L sine n theta. And what is this? This is u 2k based on this notation. Similarly, u3, which is transverse alpha 3 direction, is sigma mn eta mn sine m pi x by L cos n theta. Okay, and this is u3 mn or u3k. Okay, that is the meaning of this single expression here. Okay, so u ik is the ith component of the kth mode shape. Okay, so u1k, 2k, 3k together form one mode shape. u1k, u2k, u3k together are one mode shape. Hence the same participation factor in the three directions. Okay. Now the equations of motion come out in the form of operators like this L, I, again I can go from 1 to 3 in the three directions. They operate on the three displacements which we know now, and we put in an arbitrary damping. Okay, damping is a difficult topic, I'll talk about it briefly. Minus rho h u I double dot is minus q I. So it comes out like this with all minuses. That is why I showed you the plate example in the beginning. Okay. For example, L1 L1 U1 U2 U3 looks like 1 over A1 A2 del alpha 1 N11 A2 plus del alpha 2 N21 A1 plus N12 del A1 by del alpha 2 minus N22 del A2 by del alpha 1 plus A1 A2 Q13 by R1. Okay, this is how the L1 operator looks. So now if we represent the uith component as this sum eta k of t u I k alpha 1 alpha 2, okay, and we substitute it into the equation, we get sigma k going from, let us say, 1 to infinity. Now the operator L I operates on space, not on time, so eta k will fall out and the operator will work on u1k, u2k and u3k, because all three displacements are there in one equation. Then minus lambda, the derivative temporal comes on eta, then uik minus rho h eta k double dot uik is equal to minus qi. okay, and u1k, u2k, u3k are the mode shape components, okay. And what did we say now last time? Right here, this L3 phi mn gives me minus rho h omega square mn into phi mn, okay. So here this will give me Li operating on u1k, u2k, u3k will give me minus rho h omega square k uik. This is important, okay. So this entire thing, which this operator is complicated, you see, it is a complicated operator, but what does it do? It amounts to this, which simplifies life, okay. So if I put this into this here, what do I get? I get a sigma k equal to 1 to infinity, okay, and all are minus, so I change the sign, so I get rho h eta k double dot plus lambda eta k dot plus rho h omega square k eta k, all of them have uik common outside, is equal to qi, the external force in the ith direction, okay. So now here we use orthogonality, okay. If we use orthogonality, what do we get? We multiply here by u I another number, mode number, and integrate, okay. So we get summation k 1 to infinity rho h eta k double dot plus lambda eta k dot plus rho h omega square k eta k integral over alpha 1 alpha 2 uik uip a1 a2 d alpha 1 d alpha 2, and on the other side I have qi uip again integrated over alpha 1 alpha 2 a1 a2 d alpha 1 d alpha 2. Okay. So what happens now? This is for the ith direction. I is equal to 1, 2 and 3, all of them have the same participation factor because it is one mode, okay. So if I take the modal components in the other directions, I will get sigma k equal to 1 to infinity, the same eta k equation, integral alpha 1 alpha 2, then u in the other direction, let us say 2k, u 2p a1 a2 d alpha 1 d alpha 2, let us say this was I equal to 1, that is equal to integral again alpha 1 alpha 2 qi, the other I, let us say I equal to 2 u 2p a1 a2 d alpha 1 d alpha 2, and this part is same for all three. So if we now add up, okay, if we now add up, what happens? We get k is equal to 1 to infinity, this equation, then the summation of u1k u1p plus u2k u2p plus u3k u3p a1 a2 d alpha 1 d alpha 2. On the other side, integral alpha 1 alpha 2 q1 u1p plus q2 u2p plus q3 u3p a1 a2 d alpha 1 d alpha 2. Now this is the orthogonality condition. This is 0 if p is not equal to k. If p has to be equal to k, only one of these is selected. Okay. Now this becomes my what we call nk for p equal to k. So I have the kth fellow picked out, eta k double dot. Okay, if only one fellow got picked out, kth fellow, k and p are equal. Okay, so I get rho h, let us keep it rho h eta k dot plus lambda eta k dot plus rho h omega square k eta k into, we will call this nk. Nk is equal to integral alpha 1 alpha 2 q1 u1k q2 u2k q3 u3k a1 a2 d alpha 1 d alpha 2. Okay. Now what happens? Now if I bring this to the other side and divide by rho h, I get eta k double dot plus lambda by rho h eta k dot plus omega square k eta k is equal to 1 by rho h n k integral over alpha 1 alpha 2 q1 u1k plus q2 u2k plus q3 u3k a1 a2 d alpha 1 d alpha 2. Okay. Now this we will give it a name, we will call it f of k of t. This is like the modal force. Modal force. These are the forces. When they are integrated with a mode, they have become modal forces. This is a total modal force. Okay. And what is nk? Nk is integral alpha 1 alpha 2 u 1k squared plus u 2k squared plus u 3k squared a1 a2 d alpha 1 d alpha 2. Okay. Now we have this ODE in time. This is a temporal ODE that has to be solved, and therefore we need initial conditions. Okay, initial conditions. Okay, so what are the initial conditions? First of all, we have in each direction at t equal to 0 given by the same mode shape expansion eta k0 u I k alpha 1 alpha 2. Similarly, the velocity u I dot alpha 1 alpha 2 at t equal to 0 is the summation over k eta k dot u I k alpha 1 alpha 2. Okay. So now if we multiply this by a different mode shape and sum it up as before, okay, so what do we get? We get integral alpha 1 alpha 2 u1 alpha 1 alpha 2 times 0 u1p plus u2, so this also got multiplied by uip, u2 alpha 1 alpha 2 0 u2p plus u3 alpha 1 alpha 2 times 0 u3p, that is the left hand side, into a1 a2 d alpha 1 d alpha 2. On the right we have now a summation k going from 1 to infinity eta k at 0 and integral alpha 1 alpha 2 u1k u1p plus u2k u2p plus u3k u3p, a1 a2 d alpha 1 d alpha 2. I expanded I equal to 1 2 3 and summed them up, that is this for displacements. I can do the same for velocity. Okay. Now this is the orthogonality condition, it is 0 unless k is equal to p, then only one of them gets picked over here. Okay. So then what happens? What happens is eta k0 is equal to integral alpha 1 alpha 2 u1 alpha 1 alpha 2 0 u1p plus u2 alpha 1 alpha 2 0 u2p plus u3 alpha 1 alpha 2 0 u3p, okay, and divided by nk. So I have got my eta k0. Similarly, I can get my eta k dot 0, that will be integral alpha 1 alpha 2 u1 dot alpha 1 alpha 2 0 u1p plus u2 dot alpha 1 alpha 2 0 u2p plus u3 dot alpha 1 alpha 2 0 u3p a1 a2 d alpha 1 d alpha 2 divided by nk. So now I have my initial conditions for the eta k ODE, okay, and so eta k of t can be solved, eta k is solved. then what happens? My ui was sigma over k eta k ui k alpha 1 alpha 2 solved. Okay, that is the procedure. Okay, we have run out of time, so I'll stop this lecture here and we'll continue from here next time. Thanks.